Hi, welcome to this penultimate video on ensemble methods. So far we have seen what ensemble methods are. We have developed some intuition around random forest, understood bagging. In this video, I want to talk about boosting. So far we have seen ensemble methods can be used both for regression and classification. And then we saw what ensemble method is. It's in essence stacking together multiple models, taking in predictions from each of these individual models, and then combining all of these predictions to get a better result than any individual model. We saw how this was possible using an example. We understood how to grow random forest by taking by using a data set and replacing the rows with replacement, sampling the rows with replacement, and using these representations of data, growing multiple trees which are a little different from each other, taking the predictions from each of these trees and then combining them. We also understood what bagging or bootstrap aggregation was. This was in essence sampling with replacement of the data set, where we randomly selected rows from our data set with replacement, which might cause some of the rows to be repeated, and by this way we generate new training subsets, each a little different from the original dataset and from each other, and then we train our trees or models on each of these different datasets, and combining them together is called bagging. If all the models, each of which is trained on one of the representations of data, are trees, then we call them random forests, where at each split we also put a constraint on the features that we could use to split. In this video, I want to talk about boosting techniques. So let's get a quick recap on bagging, what bagging was, and then discuss boosting. So bagging is, in essence, we have a data set, we take samples from it repeatedly, and these samplings are done with replacement. So we generate multiple data sets, each a little different from each other, and each data set might have certain rows which are repeated, which might be repeated. It need not necessarily these data sets be of the same size as original. These might be same size as the original data set, might be smaller or might be bigger as well. There are no constraints here. So imagine, if you will, a data set of 10,000 observations. Each of these might have, let's say, 6,000, 6,000, 6,000. Because we are sampling with replacement, every time we randomly pick a row, we put that back and again pick another row. So it might be possible we pick the same row twice or thrice or 4 times even. In this way, we generate representations of the original data set, each of the representation being a little different. Now we put together models which train on each of these representations. Now one curious side effect of it is, because each model trains on a representation of data or a part of data, even if this model is allowed to be very complex, it would overfit only on a representation of this data, because bagging does not allow this model to access the original data set. It would never, though regardless how complex this model is, it would never overfit the original data. So bagging techniques often, as you would see in the hands-on video, bagging techniques get benefit when each of these models are allowed to be as complex as possible. So if these trees are allowed to grow very complex and not pruned, bagging would tend to benefit from that. Now remember, in bagging, each of the model trains on a representation of data, and even if it overfits that representation, because the model does not have access to original data, it would never fit, any of the model would never overfit the original data, and hence these type of techniques benefit usually if the models are allowed to grow complex. Now, boosting is another technique of uh, grouping together multiple algorithms. So while in bagging, what we saw was all these models grew in parallel or were stacked parallelly to each other. All of the outputs were taken from each of these models, and then we combined these outputs for a better prediction. In boosting, though, what happens is we take the original data set, we put a model, and then we choose a very simple model to start with. The output of this model would predict very few of the observations correctly because we use a very simple model. Now what happens is we would overweight the observations which were not predicted correctly, and these overweighted observations along with the original data is again passed through another model. Again the same repetition happens. The leftover observations which could not be predicted are again run through a model. So in essence we sequentially pass a model through sequentially pass the data set, I beg my pardon, through a sequence of models, each model classifying some correctly, and then we overweight the ones the model was not able to predict correctly and pass it on to the second learner. In this type of stacking where we are putting models in a serial way, usually each learner will have to wait for the previous learner to finish its prediction. And also one more thing to keep in mind is in this type of stacking where models are stacked sequentially, these type of models techniques gain benefit if each of the models are very simple. So imagine, if you will, if this model was very complex, it would mostly get all the observations correct, leaving very few for the subsequent learners, and it becomes increasingly difficult for each subsequent learner to have anything to work with. Compare that with using a very simple model where it gets some right and most of it wrong, and then the second learner has quite a lot to work on, and then it would predict some of the wrong ones correct and then pass the rest for the third learner. And so in general boosting methods benefit if each of the model used is very simple. Let's understand it using a visual example. You might understand this better. So before we go to a visual model, I wanted to talk about two basic types of boosting, two most popular types of boosting techniques. One is called AdaBoost, also known as adaptive boosting. So AdaBoost is short of adaptive boosting. The second one is gradient boosting. In adaptive boosting, the successive learners are created with a focus on ill-fitted data from previous learners. So as I was explaining, we pass the data set to a model. Whatever the model could not fit well is given more weightage and passed to the next model, and that it goes on until it reaches the last model. Multiple models are stacked together in a series. In gradient boosting though, instead of overweighting, what we pass to the second model is only the residuals from the first model. So think of residuals are when you were learning regression, you saw given a data set of points, it would tend to fit a line, and residuals in that sense would mean the distance of prediction from the actual data set. So residual is, think of it as the error in the model, so the distance between the actual one and the predicted. So in gradient boosting, the second learner gets only the residuals, it fits again, and then the leftover residual. So in sequentially, gradient boosting targets to reduce these residuals until there is a very good fit. So that is the fundamental difference between adaptive boosting, where the original data set in adaptive boosting stays the same. The data set which each model looks at stays the same. It's just that some points are attached an increased weight, the ill-fitted points are given higher weightage sequentially, and each model but still sees the same data set as the original one, though with some observations being weighted higher. In gradient boosting, the data which each model sees gets adapted or gets changed. So while the first model sees the original data, the second model would see only the residuals from the first learner. The third learner would see only the residuals from the second learner. That's the difference between adaptive boosting and gradient boosting. Don't worry about it much now if you are not able to get a hang of it. Once we see the hands on exercise, you would understand this better. Let's go through the example visually for boosting. So think of original data set like this. There are some observations classified red, some blue. Now remember I said boosting techniques would benefit from a very simple model. So simple model would just calculate Gini impurity and then draw a line. So imagine, if you will, that it draws a line like this and gets a partition on x1 if less than this point. To the left of it everything is red, to the right of it everything is blue, because that's the dominant classification. But then we don't stop here. In boosting we pass this to the next model. Here we have misclassified two of these reds. So when the next model receives this, it would feel compelled to at the least prioritize classification of these overweighted observations. So now the second learner would classify something like this. So it would say at x, let's say this was 2, this was 6. So, and this let's say this horizontal axis is x1 and vertical axis is x2. Now it would draw a line at x1 at a point greater than this point, and it would classify it like this and say to the right everything is blue, to the left everything is red. And now this is passed to the third model with these two being overweighted. Now previous ones still say overweighted. This overweighting is always relative, so relative to this, these blues would be overweighted. So now the third learner would have to prioritize correctly classifying these, and it would draw a line like this where it has correctly classified all of the blues. So if it calls this part blue, this part red, it has correctly classified this. And then when we combine the output, we end up with these. So first line comes from this, second line comes from here, model 2, and the horizontal line comes from model 3, and we take a vote. So this was predicted red by model 1, so it gets 1 vote. Here the top part gets a red by model 3, so this has 2 votes of red, this becomes red, this has 1 vote of red. And here this model predicted left part as red, so this gets 2 votes, this gets predicted as red. Here the bottom one was predicted blue, and hence this gets predicted blue. So in the same fashion, series of chops giving predictions are combined and passed together as in sequential order, with every observation which was not fitting well overweighted for the next learner. Next learner would prioritize these, classify, and we combine the outputs of all of these, and then we get something which is much better than any individual one. Now you might see, if for these kind of models to work, it reinforces what I said earlier, that these initial models, each of these individual models, have to be very rudimentary. So these learners have to be weak, so for them to draw very simple decision boundaries, and we combine these later to get a more complicated decision boundary where it is able to classify much better. So with this we conclude the theory of ensemble methods, and the next video I would show a hands-on example covering all the topics that we have learned so far on ensemble techniques, and that would conclude our series on ensemble learning. Before we move on to the hands-on example, I wanted to take a quick minute to talk about a little more advanced technique called stacking. Now this goes hand in hand with boosting and bagging. So in boosting and bagging, what we saw was we stack together multiple models. We join multiple models together either sequentially or parallelly. But mostly these need not be, but most of the time these models were homogeneous in nature. That means these came from similar family of models. Now stacking is a technique where we take, so imagine fold 1 fold 2 is our trained data. So trained data is again split into two parts, fold 1 fold 2. These might be multiple folds, but for simplicity of explanation I've just broken it into two folds. And then the test data, so this becomes train, this becomes test. Training data is further broken down into fold 1 fold 2. On fold 1 we deploy multiple heterogeneous models coming from different family. So think of it as if we deploy three models, one model might be our decision tree, second model might be our KNN, third model might be our support vector machines. Now once these models are trained on the data which was a part of fold 1, these fitted models are then used to predict from fold 2 data. The predictions are fed to a meta model. Meta model is another complicated model which would take its inputs as from the previous model. Previous model would predict on fold 2 to give the meta model its inputs. So all of the outputs from these models are fed into a meta model which again learns, and then finally we make predictions on the test data. Now usually it so happens that the meta model is usually a complicated algorithm like a neural network. So I just wanted to give you a flavor of what's coming up when we reach a stage when we study neural networks in detail. We'll pick this up again and we'll build our arsenal of techniques for our machine learning. So next video would be hands-on notebook. Thanks for watching. If you like these videos, then do please consider liking and subscribing the channel. Thank you very much.